So I'm Pavel, and I work with Dr. Stocker here at Ohio State. Um, and this paper is on range estimation of battery electric buses using hybrid modeling. Uh, yeah, are we good to get into it? Yes.
Here, fun one thing.
Yes. Yes, I'll do this one.
Okay, great.
We were very worried about it.
So as I'm sure most of you know, there's been a growing trend towards electrification in general, as well as in public transport. And there's many benefits, the environment, some cost savings, et cetera. But there's a lot of factors that impact the effectiveness of electric vehicles. They're very, especially in the extremes, weather, passenger load, number of stops, traffic can all grossly change the amount of range available for an electric vehicle. And this is all very important to consider when you're thinking of upgrading a fleet to electric. So CODA, which I'm sure you all have heard of, is thinking of doing such an upgrade. And they need to know if the buses that they're looking at, the new flyers, are going to be able to complete the routes that they already have. It's not very realistic to reorganize their entire route system around purchasing new buses, right? As a result, the goal of this project is to get a good estimate of the range of these electric buses to see whether they'll be able to meet these route requirements. The biggest challenges are going to be the limited data available for training and testing models, the limited vehicle testing, because even for a day, we'd have to pull an entire bus out of service to do testing on it, at least a day. Anyway. And there's also limited information from the supplier because it's in their interest to keep proprietary information proprietary. So it's hard for them to necessarily share as much data as we would want for creating an accurate model. As a result, the proposed approach is a hybrid model, combining a physics-based and data-driven approach to try to leverage the best parts of both. And in this case specifically, we're going to look at the regenerative braking, because that's one of the more complicated parts of the bus that's very difficult to model analytically. There's a lot of moving parts and a lot of unknowns that are not realistic to measure.
Purdue, I have a question.
I prefer to take questions at the end.
Yeah, okay.
I tend to lose my train of thought easily.
That's good. Yeah. Okay.
The starting point for this project is a physics-based backwards model developed here at CAR. And it's a component-based model that assesses the effect on energy by each component of the bus. The inputs we start with are the velocity, acceleration, and grade. And the outputs we look at are the battery SOC, state of energy, and battery power voltage, which is what we use to determine the range. The equations on which the model is based on are shown here. This is more just for reference later on if you want to come back to this. What we're going to focus on is this electric machine power component. Right now, the regenerative braking is this efficiency coefficient that's assumed to be constant, which is not very true to reality. But there's also not necessarily an easy analytical approach that will be better than this assumption. The model performs well. There are specific drawbacks, however. And when you look at the negative current region of the predictions, you see these drawbacks very clearly. The model grossly underpredicts regenerated energy, and it doesn't do so consistently. So it wouldn't be an easy fix like adding a gain or a coefficient to correct the error, right? And when you look at the distribution of errors, a vast majority of them are below zero. And that's just not good. Over the course of a route, the longer the route is, the worse that problem becomes because you're seeing more and more of this skew as time goes. The data we have available for upgrading this model, so to speak, is we have some heavy-duty dynamometer data taken here at CAR on the bus, which is high resolution, well sampled, but it's only two 20-minute test cycles. We also have some test data referred to as the drive and new flyer data. And these are good for the purposes of testing the model. However, there's gaps in the data. It's not necessarily well synchronized, and this makes it difficult and unrealistic to use for actually training a model. because those gaps, you lose information and they're not well labeled. So you don't know when the data is interpolated versus just measured. One possible approach for improving this model is to make the entire model a data-driven model. Unfortunately, this would lose all the benefits of having a physics-based component model where you can look at individual component measurements inside the model and get meaningful physical information from it. If you make the whole model a data-driven approach, like a neural network, for example, it kind of becomes a black box where you're seeing the inputs and outputs and nothing in between. As a result, we chose this hybrid modeling approach to enhance the regenerative braking parts of the model while retaining the relationships between the components of the model overall. So the data-driven implementation is limited to this electric machine section of the model here. To design a hybrid model, there's really 4 steps you can break it down into. First, you need to determine the integration of the data-driven components. There's a lot of different options. You can train a data-driven model on the errors of the physics-based components to minimize that. You can substitute components like we do in this case, etc. For a case study, substituting a component of the model allows for a good segregation between what is data-driven and what is the original physics-based model, so we can really see the effect of the changes we implement. Next, you need to generate the actual training data for the data-driven model. And this is tricky because unlike a data-driven model where you're replacing the entire process, here it's limited to a subsection of an existing model. And this means that the measured data no longer directly applies to the data-driven component. So when you train your neural network, you actually have to make sure that the data you train it with is directly relevant to what you're looking for. In this case, the regenerative braking. And we'll come back to that later on. Then you have to actually train the model. You have to determine the hyperparameters of the network, make sure that it's validating correctly. And finally, you have to verify the entire model by implementing the network into the physics-based model and make sure that the results are what you expect. A well-trained network does not necessarily correspond to a better hybrid model because the network is just looking for any pattern. And if it's not the right pattern for your physics-based model, it's going to get a worse result. So the implementation we chose, as I mentioned, was in this powertrain section of the model. And what this means for the network is these 4 are the inputs available for making the prediction. And instead of trying to get as specific as a regeneration efficiency, we actually decided to let the network model the entire electric machine power when there was regenerative braking going on. And this allowed access to better data, essentially, for training the network, because there's no real way to segregate the outputs of what we have into specifically a regeneration efficiency, right? But we can get a calculated estimate for electric machine power, as you can see here. So this is what I was talking about earlier, where the green values are what we have measured, and they don't directly correlate to what we want to train our network on. So what we did is we used individual equations with as few steps from the measured value to the desired value as possible to get our training metrics. It's important to note that you might be tempted to just take internal measurements from your original model to train the network. But unfortunately, this would just result in the same predictions as the original model because neural networks only pattern recognition. So you would just train the network to copy the original model and you would get anywhere. Instead, we split up individual equations to do the calculations for each desired input based on known parameters of the bus and known equations. And this let us get good approximations for what we want our network to predict. The network structure was chosen through the magical process of trial and error, where we tried a lot of different hyperparameters, a lot of different formats for the network, and eventually settled on these hyperparameters for the final implementation. The actual structure of the network, being a feed-forward network, lent itself to the nature of this problem being mostly a regression problem. There really wasn't a need to consider a more convoluted network than that. The network training performed very well. However, it's important to note that in some of the training, there are significant point errors that appear. And this is coming back to the fact that we really had very little data. to do the network training. I mean, once you filter the original values for relevant data to regenerative braking, that is high resolution. It was something like 180 data points, which is absurdly little, right? However, the benefit of including in a physics-based model is now we get to add physical saturations of what the motor can and cannot provide to the battery, as well as other factors that can really mitigate those point errors. So for the purposes of implementation, this training is sufficient. Like I said, though, the training's not enough. You have to verify it in the actual model. And they look good. You see the actual magnitude of the errors are actually a bit higher at times than the original model. And at first this was concerning, but the distribution of the errors is much more centered. And what this means for an integral measure, which is the state of charge, what we're looking for, is as the route goes on, because the errors are more likely to be balanced between positive and negative, the final result looks much better. The original model, like I said, most of the predicted values are below zero. And this skew adds up over time. Whereas in the hybrid model, it's about even, where it over and under predicts the desired metric, resulting in a better overall prediction. This is especially clear when you zoom in on the negative current predictions. You can see the original physics-based model, the yellow line, somewhat captures the path, right? The shape of the negative current. However, it does so inconsistently with different scales and consistently underestimates. Whereas the hybrid model is capable of following the path, but at times saturates the predictions, over predicting or under predicting over the course of the route. When we tested this model with all of the data we had, including the one that had gaps and wasn't exactly great for training, we found that it grossly outperformed the original physics-based model in almost every data set. A notable exception is this new flyer number 4. And this section of the new flyer data was almost entirely highway driving. And the highway driving was outside of the training set that was established with the dynamometer here at car. And so the neural network had to extrapolate for most of that route. And this resulted in the shakier predictions. However, for pretty much every other data set, the predictions were better, especially when it was interpolating the most common training values at like residential speeds, 20, 30, 40 miles an hour in NF1 and 2. Overall, yeah, this polar bear is here because I thought it was really cute. And he's like the symbol of the environmental benefits of electrification, right? So, you know, focus on him if you can. But overall, the hybrid model improved the accuracy of the predictions compared to the physics-based model. And what's most notable about that is the better predictions happen under sparse data. And for a data-driven approach, this is somewhat noteworthy because in most cases, you'd see a problem like this. You'd see that you don't really have a lot of data to train with, and you kind of discard data-driven approach and pursue other avenues, right? Furthermore, we did a sensitivity study on the hyperparameters versus the modeling error, and we found that there wasn't really a good correlation. Like I said before, we did trial and error for determining the network structure. And we thought, okay, well, maybe we can do a hyperparameter optimization method. Due to this lack of correlation, it's most likely that it wouldn't be any better than just trial and error for finding a network structure. In the future, it would be honestly interesting more than anything to recalibrate the entire model based on this new, better negative current prediction and see those results reflected in the entire state of charge predictions for the model, since they weren't really directly relevant to the hybrid model creation. And it would also be interesting to try and include some of these physical constraints to the network creation, where you eliminate some of those point errors in the training process, rather than relying on the physics-based model to mitigate them instead. This can be done through physics-informed neural networks or other methods where you try and take into account some of the physical restrictions of the problem. But that is all I have for now. Are there any questions?
Yeah.
Back to slide 3.
Yes.
So the Excelsior, is that a brand for this electric bus?
So the brand is New Flyer, and I think Excelsior is one of their lines of buses.
Okay.
Um,
So the other half of the question, they've already got, I've ridden on the electric buses. They're really good. They're quiet.
yes.
So does Coda have a working analytical model that they use to figure out how much electricity they're gonna need or?
No, and that was, I think the driving force behind why they approached Carr to do some of this
They don't
predictive
have
work.
one yet. Yeah,
I don't think so. It's been a while since we've been in touch with Coda directly though, and a lot of that preliminary work was before my time creating the physics-based model. My part was kind of taking it a step further and trying to improve based on the adaptive approach.
last question.
Yeah.
Delaware has school buses, electric school buses.
Okay.
Does this analytical neural network apply to that type of driving?
Yes, a very nice part of this model, one of the benefits of the physics-based part is by changing the parameters of the bus to the parameters of the school buses.
Yeah.
You could very easily transpose this modeling onto that new situation. It might take retraining the neural network depending on how different the two buses are and how they behave. But overall, it would be relatively trivial to go from one situation to another.
Thank you.
Any other questions?
Oh, that is true. Dating.
Well, nobody has questions about the.
Any more question from you? Oh, wait, somebody raised their hand. That's what it is. Yes.
I don't know how to.
Just not.
Yeah, I can't. Yeah, from here. Because
No, I can only disable mic. No. So if you have a question from the audience, you might need to type it in the chat because we cannot unmute you. I can try, but. Wait, maybe I can. It says disable mic. I need to make them a presenter. Sure, now you're a presenter. Okay. So, all right, if you have a question from the online audience, you should be able to unmute yourself if you have a question. Oh, you can stop sharing. Or like minimize it, there we go. I don't know how to do this.
How did this part?
Okay, well, we're gonna assume that there are no questions. I allow the student to unmute themselves. Okay. All right,
Sorry about that.
that would be nothing. All right, well,
Yeah, then if not. I think
If not,
we're
good to
good
go.
move our-
Oh, wait.
Presenter.
yes, so Patty confirmed that, yes. Yes.
Okay, one more question.
Yeah.
For Coda, when I go on their electric buses, the 23s and the 2400s.
Yeah.
I ask them how many miles they have on them. Most of them have less than 2,000 miles right now. So when would you apply, how many miles do you want to have on the bus before this is accurate?
Well,
Or is it a brand new bus would be just as good?
ideally, it should work on the bus no matter how many miles it has on it.
Okay.
Realistically, the quality of prediction is gonna change as the bus ages. And the battery's not gonna do quite as well, components are gonna wear, efficiencies are gonna get worse, maybe better in some cases. And it's gonna change how accurate the model is, but
Yeah.
not as much, like, it shouldn't be a very dramatic effect.
Okay.
If you look directly between a bus that has 2,000 and 200,000 miles on it, you're definitely gonna see a difference. But ideally, this model is pretty well functioning from the time the bus is new to any reasonable amount of wear. The nice part about it being physics-based though, is you can then retrain it when it no longer accurately reflects the buses in service. You try to account for some of those changed efficiencies.
Okay, thank you.
Okay. Take our presenter and then next. um, Or you can use the same Zoom and then
Let me just email it to you.
I'll log you out.
Okay, yeah, I'll pull it up for you.
I'll log out.
And you are muted on Teams.
Yeah.
For now.
Oh,
So when
you
it
saw
starts-
me, I was like, yes, of course.
Yeah.
Still muted.
No.
Yeah, I'm good.
Okay. All right.
Hello everyone, my name is Abhishek. I'm a third year PhD student here at CAR. Dr. Marcelo Canova is my advisor. This is work which we did along with Hyundai Motor Company as part of a project which we are doing with them. Talk you through the details for now. So just to give you a brief outline of what I want to talk about. First, I'm going to tell you what are batteries, what happens inside them, what is the context which is related to this work, just to give an understanding of how this work is relevant. And then I'll talk to you about what are the current methodologies which are used along these lines. And then as part of this work, we developed a new methodology to understand what happens inside the batteries better and relate it to real life applications. And then I'll talk about conclusion and some future work. So firstly, batteries. As we all have heard, like in the questions earlier as well, batteries age. As you use them, as years go by, batteries age through, so many mechanisms you see over here. But research or the literature, the whole battery community puts all of these mechanisms into three categories. Loss of lithium inventory, which I'll be referring to as LLI in the presentation. Then there's loss of active material in the negative electrode and the positive electrode. So these are three distinct modes of degradation, which majority of the research community categorizes them into. Now, going into the techniques which are relevant to the work which I'm going to present about, the major technique which is relevant is differential capacity analysis. It is a completely non-destructive technique which is used by the research community to identify how the battery behavior is changing. Like for example, so differential capacity analysis is basically another word for DQDV. It is basically the rate of change of the capacity of the battery to the rate of change in voltage, which you see over here. On the y-axis is the rate of change in capacity, and then you have the voltage on the x-axis. And the peaks and the valleys you see in these plots, they represent various chemical reactions occurring inside the battery. Each valley or each peak corresponds to a particular phase change. So this basically gives you a brief context of various analysis which we do using these techniques. Coming to the motivation of the work. So a lot of research has been done which uses the technique which I presented earlier to talk about how the battery is aging, like which of the mechanism is occurring in the battery by theoretically simulating those techniques. But there's no research that connects these non-destructive technique to the proper electrochemical modeling of the battery, which is used to design the batteries. So that's a gap which we wanted to bridge as part of this research. And while working on that, majority of the experimental data which is available right now is under lab conditions, while our work, it uses battery cells extracted from EVs which are driven across in the real world. So talking about the experimental data which we collected for this, we tested this. We developed this methodology using two cells. I can't reveal the capacity of the cells, but these are large format cells which are used in electric vehicles flying in the real world. So we extracted cells from multiple vehicles which have different kilometers on them. Over in this part, I'm going to talk about two cells mainly. First one is something which is extracted 100,000 kilometers, and then 250,000 kilometers. And then of course we have a baseline cell included in the study to generate results. You see over here, we basically tested these cells at a C rate of C over 20, which basically says that it takes 20 hours to discharge the cell from 100% to 0%, and it is tested at 25 degrees Celsius. The plots you see over here is basically the experimental data. As you can see, you go from fresh cell to the 100K to the 250K. There's close to a degradation of 12% at the end of 250,000 kilometers. And the same plots are analyzed, just doing simple mathematics to generate generate the DQDB plots you see over here. So this is basically the whole experimental setup we used for this project. Now, going to the next stage, like I mentioned earlier, what we wanted to do was bridge the gap between experiments and theoretical studies to the modeling of batteries. So the model which we used over here is called the ESPM. It's the extended single particle model. It's a complicated model with lots of partial differential equations. I'm not going to go into those details. But what I want to highlight in this is a lot of parameters in this model are estimated roughly. Like they use optimization techniques, they use some experimental techniques for some parameters like the particle radius. But there are a few parameters which cannot be tested without opening up the battery or tearing it down and doing experiments on it. So for those parameters, researchers usually employ optimization techniques to generate that. Now, the gap which we wanted to bridge was basically using aged experimental data like the one you see in this slide, and using that data to generate proper results for this optimization. Yeah. So, all right. So that is basically the gap which we wanted to bridge in this part. So going forward, the first thing which we always need to do is calibrate an electrochemical model. At the beginning of life is when the model is usually calibrated, where you actually have all the data you need in terms of the electrode properties, the particle radius, the concentrations, so on and so forth. And even having all of that data, it still leaves you with some parameters which need to be calibrated in the electrochemical model, which I showed you earlier. So this is the beginning of life calibration for the cell which we have right now. We had an RMS error of 8.4 millivolts at the beginning of life. And this table basically shows some 4 of the main parameters which are calibrated at beginning of life. Now, what we wanted to do at this stage was basically estimate what are the degradation mechanisms that are happening in the aged cells. So, and how are the calibration parameters affected because of the aging. So the methodology which we developed is basically divided into 3 parts. First one is basically bridging the gap between the aging mechanisms in real life and the parameters in the electrochemical model which affect this in simulation world. And once we do that, then we wanted to decouple all the aging mechanisms in the cells so that we can understand how much of aging has occurred due to each mechanism in the battery. And once we do that, then our last objective was to quantify the effect of each mechanism on the battery parameters, basically the parameters which I showed you in the previous slide. So I'm going to quickly talk you through these 3 steps for now. The first step, like I said, is identifying the model parameters. So the way we did was like I mentioned, there are 3 different mechanisms: LLI, LM in the negative electrode and the positive electrode. We did different analyses to identify which of the electrochemical model parameter directly affects each mechanism the most. So the equation which you see over here is just the theoretical capacity equation, which applies for both the positive and the negative electrode. And the plot you see on the left is a plot which is developed using theory which is relevant to loss of lithium inventory. The loss of lithium inventory basically says that the negative electrode OCP curve in layman terms moves to the left. And what we wanted to do was what is the parameter in the electrochemical model that will generate the same effect as what you see is supposed to happen theoretically. So we did multiple studies, sensitivity analysis, so on and so forth. And going to the end result, we realized we came to the conclusion that the initial lithium concentration in the negative electrode is what affects the loss of lithium inventory. And going to loss of active material in the negative electrode and positive electrode, we used the similar approach to understand which parameter affects LAM, and the active material volume fraction and the negative electrode and positive electrode affect these two mechanisms correspondingly. So at this stage, we basically finished the first step where we know what are the parameters in the electrochemical model that affect the degradation mechanisms directly. Now, the second step is basically understanding how much each mechanism is there in the cell, and that is probably one of the hardest parts when you're trying to do battery diagnosis and taking in. So what we did was we used something which we optimization folks love, the necessity and the sufficiency conditions. So whenever there's a mechanism, whenever we wanted to understand what mechanism is there, we asked two questions about it. Is the mechanism necessary to explain the behavior of the aged cell? And if the mechanism is indeed necessary, then is it sufficient to explain the behavior? And if these two questions are answered correctly for that mechanism, like let's say if LLI is necessary and also and if it is not sufficient to explain it, then LLI is definitely there in the cell. That is the kind of approach which we have taken to decouple the degradation mechanisms. The way literature usually does it is it breaks open the cell and and people run the electrodes through a bunch of characterization experiments to come up with these final answers. But the whole point was to generate a non-destructive technique to identify these mechanisms. So going forward, what the first step was to decouple all these mechanisms, like I mentioned earlier. So we answered both of those questions for each of the three mechanisms. Like for example, LLI. The plot you see on the left is basically the DQD plot comparing the fresh cell and the aged cell. So the blue one is fresh and the orange one is the aged. And you see how in the aged cell the peaks and the valleys are moving. But when you simulate LLI using an electrochemical model, you see there's one major difference between these two plots. The value over here, it does not move downwards. So that basically tells us that LLI itself is not sufficient to explain the behavior of the aged cell. But to answer the first question, this is an analysis which is developed iteratively. I'm just going straight to the conclusion. The shift you see in this peak to the right, this major shift is possible only because of loss of lithium inventory in the cell. Loss of active material will not create a shift as big as this. So that is why we decided LLI is definitely there in the aged cell. So once we know that LLI is there in the aged cell, and like we established earlier that the parameter initial lithium concentration affects LLI, we went ahead and estimated the amount of CN0 or calibrated CN0 in the aged cell using simple grid search techniques. We have a cost function which basically optimizes CN0 by minimizing the error of movement at this peak. And a simple grid search gave us CN0 to be 2.65 eForce on. And now that we have CN0, the next step was to talk about lots of active material in both the electrodes. Coming to the negative electrode, we asked both of the questions again, and we see that a major difference happens because of this peak, where LAM does not cause the increase in intensity, but we have see it in the experimental data. So we definitely need LAM. LMNE alone is not sufficient, and the peak movement over here where it comes down, that is possible only because of loss of active material in the negative electrode, and that answers the question that loss of active material in the negative electrode is needed. And then we go ahead we have a new cost function in this case where we are optimizing the epsilon, the parameter which is related to LAM, and the cost function is basically an RMS error between the experimental voltage and the model fit, and we estimate epsilon m. And then we go forward to the loss of active metal in the positive electrode. We ask the same questions again. LAMPE gives a completely different behavior compared to LLI. And answering those two questions, we realize that LAMPE is also definitely needed in the cell. And now that we go ahead, we rerun the optimization to estimate epsilon P using the previous calibration. And it's the same cost function, and we generate all the results for the calibration for the age cell. So this we generated this methodology and generated the basic calibration at 100K kilometer cell. We tested this methodology on a 250K kilometer cell to see how the results come, whether they are following the trend according to the literature. And we see that the methodology actually works for the 250K kilometer cell as well. So earlier, like I mentioned, the main advantage of this methodology is just to be able to estimate these parameters at an age stage without resorting to destructing techniques, and being able to understand how aging affects the electrochemical model parameters. So going forward, so that, like I said, it helps us figure out calibration at the age stage. The work which is happening right now is we are validating the results which we obtained using post-mortem characterization, which is basically destructive techniques. And also, we are also looking at the aging model simulations where each of these mechanisms actually has an equation and how these parameters are varied if you actually simulate the model using those techniques. Yeah, so that's all I have. It's fast. Any questions?
Slide 7, please. So the chart on the right,
Yeah.
are all those at least 4 years old? The
Yes.
age batteries are at least 4 years.
Yes, the age batteries are at least 4 years.
Okay, thank you.
You go back to the results slide, I don't remember what number it was. Yeah, so I'm a little confused how you determine that it provided consistent results.
So one thing which we mainly wanted to look at was the trend of these parameters. Like, when a cell is aging, these three parameters are technically supposed to reduce. That is one major trend which we wanted to notice. I've only shown the data for 2 cells over here, but we had cells at 5 different mileages when we developed this. So that is one thing which we wanted to check. And again, like I mentioned, what part of this work was also validated by running proper aging model simulations and comparing the results with that.
Okay.
What are the variation, like if there are same cells which do 100K cycles or like 100K
Yes.
miles, will they have the same aging or like?
Yes. So for 100K and 50K, we had 2 cells each, which we generated results on both of them separately. As expected, there are differences between the results for both of these cells.
Yes.
That is, it can be manufacturing, or it can be they are taken from the different vehicles, or there can be so many reasons to that, but they're not aged in the same way.
So is there a way in which we, like, if you know how those cells performed like in their till that point, can you take that into account to determine, okay, what should be these parameters if you
Yes.
have that information?
Definitely. So the other thing which I probably missed mentioning was the cells which we have over here, the 100K and 50K, we do not have any prior driving history. Like, we do not know the number of cycles they have been through. We do not know the current profiles they have been through. We only just have the cell without any history. So we cannot actually simulate what happened over there. But like you mentioned, if you have a specific driving history, then you can simulate it using electrochemical models and scenarios.
Questions? All right, thank you. Any question from the online audience? Please type them in the chat. Don't raise your hand. That was not easy. Just Q&A. They clicked on it before. Alright, sounds good. You click on the wall. See it. Well, there's only. Alright, I think we need to fix it. Alright, thank you, everyone.